Okay, well, thank you everybody for being here. I am she. I'm Anne-Marie Hoskinson, and I'm currently a science teaching fellow in eBio, along with Sarah Wise. And before that, I taught at a couple of different places, and I'm going to tell you about a little bit of the work that I did at where I was previously in Minnesota. And what I've prepared today is, in the spirit of the new DBER, right? What I hope will be a short talk that will stimulate lots of great thought. Usually when I talk to people about misconceptions and case studies, there's lots and lots of discussion. So that's really where I envision most of our focus being today. So to support that, let me give you sort of the outline of what I did and what the foundation for that is before we sort of go off on that tangent. And I'm going to seriously leap right in here. And let's entertain this question of what is a misconception to begin with, right? So it's not a trivial question. If I'm going to be talking about misconceptions and case studies, let's go ahead and define them. One thing that you will notice if you decide to look at the literature on this subject is that there are different characterizations for what people are essentially equating. And I don't think that's the right thing to do, but you'll see these terms bandied about and sort of meaning the same thing to a lot of different people. A naive conception, an incomplete conception, a novice conception, right? So there isn't a good consensus in any of the discipline-based education research that I've looked into, primarily biology and then secondarily physics. However, there are some characteristics that I'm going to attribute to the misconceptions I'll be talking about today. And the first one is that the misconceptions that we're interested in are somehow more pervasive and more persistent among the population. I know those mean two different things. By pervasive, I mean those misconceptions that are widely held by many different novice learners of varying socioeconomic background, of varying educational preparation, independent of standardized test scores like SATs and GREs. Okay, so there is some commonality to, and I'll give you some examples in a second, to the particularly pervasive misconceptions I'm going to be talking about. The other characteristic that they often have is that they're really robust to change, right? So as they're independent of the learner's motivation or the teacher's either motivation or intervention methods or talent or other external factors, right? Or the environment or the richness of the teaching materials. So here again, there is some quality of this conception that is independent of external factors. Right? So those are the only two claims I'm making about the ones that are more interesting to study. So what am I talking about here? So let's start with the sort of trivial one. So a misconception could be based on incomplete or missing knowledge, like blood vessels have valves, right? All a student needs to do there in the best world is read a sentence in a book or hear a teacher say something such as veins but not arteries have valves, right? Veins but not arteries have valves. So the student, sort of transparent to them, they kind of go, oh wait, not all blood vessels have valves, only veins do. Okay, so that's a piece of incomplete or missing knowledge, right? Take the correct concept, plug it in, you've got a complete idea. Simplification, of course, but the other possibility here.
That's not a concept.
One would argue that that's not a misconception. If it's not.
But it's not a concept; it's a fact, right? So veins and arteries could both have valves.
Well, so I'm not gonna. That's a really interesting piece of the literature to get into. Is what indeed constitutes a concept versus a fact versus an idea, and I don't think that's trivial at all. I'm not going to go down that path today. The other possibility here with misconceptions, and now we're starting to get into some kind of rich territory for us as teachers and practitioners are these flawed mental models that students have, right? So by flawed mental model, what I mean is a mental model that is coherent and can therefore be used to make predictions, even though the predictions that come out of that model will be incorrect, scientifically speaking. So a good example of this was there was some discussion on the DBER list last weekend about Private Universe, which was I think it was a PBS series in the late 1980s. And one of the concepts there was based on a flawed mental model of how seasons happen, right? So there were several examples of this. So where I think that it's really rich to be thinking about misconceptions is this idea of, and it sounds really trivial, miscategorization. To my interpreting the literature and sort of going off on my own, I'm not going to do too much of this right now. Maybe we can get into the discussion. It seems like a couple of the big categories that these fall into are when, say, young physics novices, right, often attribute properties of thingness or entities to what are actually processes. So they interpret force as a thing, right, a thing to be used up. And they interpret heat as a thing that flows, right? It goes out the door, right? So that's one kind of miscategorization. Miscategorizing a thing, or I'm sorry, something that is a process as a thing, or giving it thingness. And then the other one that's particularly interesting to me as a biologist are the distinctions between certain kinds of processes. And what I'm calling these processes are direct processes versus emergent processes. So a direct process would be, you throw a ball through a window and the window breaks. The agent is the baseball, and the cause is, the outcome is a broken window, right? I'm using very simple examples to sort of illustrate the point. Emergent processes are really pervasive in biology, especially. And emergent processes have to do with properties like, there being many causal agents, and all of them having the same force on the outcome. So what do I mean by that? Well, in a population, right, all of those individuals do act independent of one another, but pooled together, they produce a distributive effect in the outcome of some metric of that population, whether it's growth or decline or something like that. A common one that we see in teaching about natural selection and evolution, and this is from like the introductory level all the way through the upper levels, is that mutations arise from organismal need, right? So students, the way that they've got it wired, for lack of being colloquial there, the way that they have this kind of concept wired is that the causal agent is some change in the environment that then invokes in the individual some change resulting in a benefit to that organism, right? Or another one, the diffusion is a mass action, but the way that students have it characterized is that oxygen is being pulled from the lungs into the bloodstream by some gradient, right? The gradient is doing the pulling. Okay, so what are the costs then? We'll return to that idea, but the classroom costs here, and these are pretty well established. I'm not making any crazy claims here. With novices, they're already penalized by having lower metacognition and lower ability to reflect about what they know and what they don't know. And these particular persistent misconceptions are really resistant to teacher intervention. So like I said, it isn't us, right? And it's not the student either. It's not a lack of motivation. It's not a lack of wanting to learn. It's something about that conception. And I posit here that some of these science-specific processes are persistent, particularly because they don't line up with sort of common everyday experiences, which is how most students, most novices, start to categorize their thinking. Okay, so that's a brief overview of misconception. Now, what is a case, right? So, case studies in science. There are a lot of concepts about this, or conceptions about this too. I am claiming only that a case study has two elements. There is a story that sets up a problem to be solved. A story that sets up a problem to be solved. So the story is kind of that's a powerful human construct. And I mean, if you go to Google Scholar and type in power of story, the first 20 hits you get have nothing to do with science, right? They're all marketing and business and history and political science. And it's obvious that story has a really important place in human learning, right? And then the problem is just a scenario or some kind of exercise that our novice learners have to go through in order to get to an outcome that they don't anticipate yet, right? They don't know how to get there yet. So one way to kind of think about these, and this is my construct here, so I'm not claiming that these two axes are orthogonal, but I'm claiming that it is a good way to sort of think about how cases are organized. So, and one of the ways we can do that is to look at how much student direction or constructivism is involved in them changing their concepts and learning, right, from less to more constructivism. And then looking also at the problem complexity and going from low to high on that scale. So clicker cases are usually of low problem complexity and kind of less on the scale, lower on the scale of student constructivism. Not always, okay, not every clicker case. And whereas something like simulations or setting up a modeling simulation, the problem complexity is higher there, and it's more up to the student to construct their own knowledge of a problem solution there. So the interesting question to me about this combination is, what are the mechanisms? We know case studies are effective. There are literally thousands, over 6,000 it was the last review I read, studies looking at the effectiveness of case studies teaching in science, okay, and looking at everything from biology to physics to mathematics, engineering, chemistry. So there isn't a whole lot of dissonance about the effectiveness of case studies, right? The best clicker case study is more effective at helping students learn in general, on average, than the best lecture that's really engaging. So what isn't being asked is, what are the mechanisms? What is it about a case study that helps students learn, right? And there could be a lot of different elements. Is it the story setup? Is it time on task? Just that they're working on something instead of passively being little sponges. I suspect for the intersection of case studies and misconceptions that there's something in how the problem is set up. Okay.
Yep. It was a little interlude.
And you're getting this on film.
I was off 2 degrees.
Oh crap, another misnomer.
So I think that two really essential things here are how the problem is set up and the fact that for really effective case studies, there's student discussion, right? So it's not a model where there's one expert and 500 passive novices sort of absorbing information. There is student discussion about what their concept is and what their justification is. And a lot of people in this room have done really important research about the importance of students engaging with one another. So my question for this particular study was, could this combination of case studies with instant feedback, which I'll tell you about in a second, help to dismantle the incorrect conceptions and replace it with the correct one, right? So the methods for this, this was 2 semesters of, over 2 semesters, a 1 semester introductory biology course, 1 semester in the spring of '09 and the subsequent one in the fall. Each section got a pretest, the same pretest as a matter of fact, that included some really common misconceptions. And sources for that included some work that's been done at the University of New Hampshire for ecology studies, and I got some actually from Jenny Knight, and you know they have been validated. They're good questions. The treatment differences here. So this is a pseudo-random study. In the spring of '09, they got the regular old interactive lectures, and by interactive lectures I mean not just me stage on a stage, but you know, think, pair, share, here and there kind of thing. Whereas in the fall of 2009, I picked 3 what I thought at the time were very persistent misconceptions, and targeted those 3 persistent misconceptions with a combination of a case study and a tool called Instant Feedback Assessment Tool, or IFAT. And so how that works, why don't you guys I'll just share these in pairs if you would. What I'm passing out are these examples of IFATs. Don't do anything with them yet. But how the setup would work in a class was students would get an interactive case. And here's an example. This is not one of the ones for the misconception. But here's an example of one where the objectives were to learn about trophic webs and to make predictions about the consequences of removing one of the organisms in the trophic web. So I would start with a slide like this, and students could also download this ahead of time. And in small groups, I would have them draw arrows showing the interactions between the organisms in the group. So already it's a little bit different than just showing them a web, because as you can see, I have this all mashed up, right? There aren't obvious trophic levels. That's also on purpose. Then the subsequent part was to give them this IFAT. And the way these things work, and I'll show you, you'll actually get a chance to do this in a second, is that they're really similar to clickers in some ways. So students would get on the screen, I'll show you in a minute, a multiple choice question. And then in their small groups, they'd have one of these IFATs that you've got in front of them. And they'd discuss and come to a consensus on a question before scratching it off, right? It's just like a little lottery ticket. If they get the question right, then there's a star underneath it, and yay, they get full credit. If they get it wrong on the first try, they can try again, right? So in essence, they're self-generating and self-correcting. So they're not waiting for a clicker question to be answered on the screen. And really importantly, unless they have a tyrant in their group, they really have to. They're forced to come to a consensus before they scratch that thing off. And I tried to find I have some video clips of some of the interactions, and they get really passionate. I mean, we're talking about 5 lousy points out of 750 for the whole semester, right? They get really passionate about arguing for their answers before no, don't scratch it yet. I know I'm right, because so in some ways the interactions are much different than clicker questions. Also, from a practical point of view, we didn't have clickers that year, so I was kind of stuck with these. So here's an example of what might happen, and you guys can work quickly on this. So they've seen a few graphs, and what I show them is, this is a graph from, I actually pulled this particular case from the primary literature. There's more of it out here, and I tell them that their task is to predict what's going to happen to these mesopredators. So those are things like in the badger, for you non-biologist people, the not quite keystone top level predators. So what's going to happen to the mesopredators in this removal experiment, right? So go ahead and just do this for a second.
Coyote is the top predator.
Coyote is the top predator. Coyotes are being removed. What's going to happen to the mesopredators? Yep, use the graph to make predictions. I'll show you. Yes, so the graphs here. So here's mesopredator populations, right? So what's going to happen to this line after the coyotes are removed right here? Will this line go up, or will it go down, or will it stay about the same?
I don't know.
Don't scratch!
Hey, Anne-Marie.
I'm ready to
Yes, absolutely. When you think you got the answer, scratch it off and see if you're right. Did you guys get it right?
Well, let's look at the graph.
You have to see what else.
All right, folks, come to a consensus. Scratch off your answer and see what you get.
That would get it.
It's kind of satisfying.
It's more time.
All right, has everybody reached a consensus? Student groups. No, student groups. Right. So you have to work together. You have to reach a consensus. All right. So next slide is where they see their prediction, and so you've already gotten it right, and now this is a point of discussion. So why were you right? Right. What's going on with this graph? So as we work through the case study here. Now I'm going really fast and I'm skipping some stuff. And then we might come to a graph here, and in the interest of time, I'm going to kind of skip over the question. We might come to a graph here where now my expectation with this is for them to really assimilate the knowledge that they've seen so far that you haven't about coyote removal and about food webs. They've seen the graph about mesopredators. Now I'm asking them to predict, or I'm sorry, to interpret what's going on with this graph, right? So we spend some time with this first and dissecting the thing. They need help reading the axes. They need help understanding, what those bars mean. And then I turn them loose and have them actually choose what the best interpretation is. And go ahead and do this if you want to, but
The treatment is removing coyotes.
yes, right. So control sites and removal.
That you're assuming there's no interaction.
It seems like coyotes directly away.
What is weird is first it goes up and then it
We're saying, this is from mesopredator.
Yeah, that's right. Because I don't think C can't use nothing about mesopredator. That's true. You can't. Yeah, there's no effect on this graph. It just says coyotes. So I think these. Yeah, okay.
it's hard to know what's going on because the control is dropping. Too old for this. Heart can't take it anymore. I don't know. I can't.
So this one is usually kind of a tough one for students, and we'll kind of, what I might do, in fact what I did do according to my teaching notes, was eliminate one of the answers to help them narrow things down, right? So is there anything that we can pull out of this graph about coyotes and their choosiness of which rodents they eat.
I would say you don't have direct evidence for that. It's more like a corollary.
Inference.
An inference.
An inference, right. Yeah, so you're right, it is an inference, and if we're looking for the best interpretation, I might coach my students. Then let's go ahead and eliminate that and look at the other
What
ones.
do we know
right?
about rodent diversity?
Or what do we know about rodent
But what do
diversity?
we know about rodent diversity?
You
in
don't
this
know
population
anything except
anyway?
this.
Is it 3 different kinds of rodents, or is it 47 different kinds of rodents?
Right, so that's a question that comes out during the discussion too, right? So I'm being really glossy here, but the point is that eventually students would get to a point. Does anybody want to try a scratch off here before I go on? You're almost ready to choose? If you're almost ready to choose, go ahead and do it.
We chose.
Right?
They don't all have stars underneath it.
Right. So the opportunity here is to have students interact, and be able to call on a group because they've already discussed it, right? To be able to call on a group and say, why was your answer B correct? What did you guys think about that? Now, here again, the advantage is sometimes when we call on students in clicker groups, they're not sure. They think they know, but they're not sure. And by giving students something more tangible to discuss, tangible isn't the right word, more concrete to discuss, it gives them a boost of confidence so that they feel like they know something when they're talking, to the rest of the group. So this is in essence, this is there's a case study in 3 slides, right? So let's get to the cheese. What were the learning gains here? I'm going to let you digest this for a minute. So here's what you're looking at. The green bars are the pre and post testing for the spring of '09, which was effectively the control case. So no case studies, it was just interactive lectures. The blue bars are for fall of 2009, which was the treatment of case studies followed by IFATs. The 3 misconceptions were the same across both semesters. And the ones that I chose were the dominant traits are the best and most common in a population, that there is perfect energy transfer among trophic levels. This is a really common one for not only our introductory biology students, but upper level ecology students. And that there's no difference in the products of mitosis and meiosis. Okay, that's the misconception. So what you can see is that in spring of '09, there was really no effect. This difference is not significant, although it's disheartening. There's really no effect on the misconception of an interactive lecture.
So these are measured by
Pre and
choices
post
on
testing.
on
Yep.
multiple choice tests.
Multiple choice exams.
Have you
the
ever
numbers
asked
down
somebody
here.
to explain why dominant traits are
I'll
not
get
the
there.
most common?
Yeah. That's a really good question. But what you can see in fall of '09 is that there was tremendous improvement in learning with the addition of the case study IFAT approach. Now, because I know that you guys are really sharp, I know you're thinking, well, was it the case study or was it the IFAT? I didn't have, at the time I constructed this study, it was kind of on the fly, right? And I didn't have a perfect control of doing, just a case study with no measurement after that, and then just an IFAT. Although I did look at some of my teaching notes and pulled out a couple of others for the fall of '09, right? So these are learning gains from the IFATs only. They have a significant effect. Both of these differences are significant. Just the IFATs alone, right? No case study, just IFATs on different misconceptions here. So what I conclude from just that little bit of data is that this combination of case studies and incident feedback, like you guys did, does result in better learning and retention. Oh, and I did forget to say that the time delay here was between, let's see, 5 to 11 weeks between the case study in IFAD intervention and the post-test on the final exam. So that's a pretty long time for them to be holding on to this. The other conclusion is that the effect varies based on the misconception, right? And this is where, I mean, if we wanted to, we can have a discussion about this for the remainder of our time. And really, you know, what for future work, how is knowledge misconceived, right? How does it get to be in the wrong category or get to be misconceived in the first place? What constitutes an actual change? So how do we know that it's gone from misconception to correct conception, right? So like Mike's question was asking, sure, they can spit back to me that a dominant gene is not the most common in a population necessarily, and that the distinction there is that it only takes one copy of the allele for the trait to be expressed. But if I ask them some application question, will they nail that? Has that conception actually changed? Why are some misconceptions really resilient to change, right? So why this one, but that one I can talk my way through it. And then really one of the things I'm interested in is what are the instructional interventions that work? Why did this case study IFAD combination work? What is it about that construct that helps my students learn, you know, to the point where this is nothing to be, you know, raving about here, but it's significantly higher than the pretest, and it's significantly better than I did in the semester before, where I actually did some damage there.
Hey, Anne-Marie.
So those are, yeah.
Quick question.
Yes.
Sorry to interrupt you.
I'm done. That's it.
Oh, okay.
So.